What if a 36-year-old telescope, the kind of machine most people had already written off as living on borrowed time, just quietly broke the internet with 3 discoveries in 6 weeks that nobody saw coming? That is exactly what just happened. And the result is one of the most remarkable stretches of science Hubble has produced in years. Before we go any further, do something for me real quick. Tap that like button right now. Not in a minute, not after the video, right now. Then hit subscribe and ring the bell so this kind of deep dive finds you the next time something this big lands. And forward this to one friend who always asks you, "So what did space do this week?" You know exactly who I mean. All right, let's get into it. Let me set the stage. In the span of roughly 6 weeks this summer, Hubble did 3 things that have astronomers genuinely excited. It found a black hole that everyone assumed was impossible to detect, hiding in plain sight inside one of the most famous star clusters in the sky. It confirmed that our nearest large galactic neighbor, the Andromeda Galaxy, the one you can actually see with your own eyes on a dark night, has been quietly dying for the last 500 million years. And it caught a galaxy more than 12 billion light years away, doing something right now that once changed the entire universe from dark and foggy to bright and clear. 3 discoveries, 6 weeks. 1 telescope that was almost written off as a near failure when it launched because its mirror had been ground to the wrong shape. Imagine that. The same machine, fixed by astronauts in orbit 3 decades ago, is still reshaping what we know about reality. Let me walk you through each story in plain language so you feel the weight of what just happened. The first discovery came out on July 13th, 2026, in a paper led by Matthew Whitaker and Anil Seth at the University of Utah. To understand why it matters, you have to know the place where it happened. The place is called Omega Centauri. It is not just any star cluster. It is the most massive globular cluster orbiting the Milky Way. Roughly 10 million stars, all gravitationally bound, packed into a ball about 150 light years across, older than almost anything else we can see in our neighborhood of space. Many astronomers believe Omega Centauri is not actually a true globular cluster at all. They think it is the surviving nuclear core of an entire dwarf galaxy that our Milky Way tore apart and swallowed billions of years ago, stripping away the outer stars and leaving behind only the dense central heart. That would explain why it is so unusually massive, so old, and so strange compared to every other cluster out there. It is essentially a galaxy's corpse, still glowing in the dark. Now here is where the puzzle sat for decades. Based on how massive stars live and die, supernovae exploding and collapsing inward, Omega Centauri ought to contain around 10,000 stellar mass black holes. That is the number the theoretical models have predicted for years. Black holes left behind when big stars burned out and fell in on themselves. The problem was that nobody had ever actually found a single one. Not one. 0 out of an expected 10,000. Decades of searches using radio signals from material falling into black holes. Decades of searches using X-ray bursts from stuff getting shredded at the event horizon. Searches using radial velocity, watching for stars wobbling in response to an unseen companion. Every standard approach came back empty. Either the models were badly wrong, or the methods were missing something fundamental. The so-called missing black hole problem became one of those quiet embarrassments that astronomers kept in the back of their minds, hoping someone would eventually figure it out. The Utah team decided to try something different, something slow, something patient. They went back through more than 20 years of Hubble's archived observations, pictures Hubble quietly took between roughly 2003 and 2023, and instead of searching for radiation pouring out of black holes, they watched a single star. They tracked its precise position, year after year, with the kind of measurement discipline that only a long-running space telescope can deliver. That technique has a name. It is called astrometry. The basic idea is simple. If an invisible companion with real gravity is tugging on that star, the star's path across the sky will wobble in a predictable way. You just have to measure carefully enough and wait long enough to see the wobble clearly. And the data showed it. A wobble. Tiny, but unmistakable across 2 decades of careful measurement. The kinematic fingerprint of something invisible pulling on that star. To nail down the answer, the team brought in fresh observations from the James Webb Space Telescope, which sees the universe in infrared light, and combined that with all of Hubble's ultraviolet and visible measurements. 2 completely different telescopes, 2 completely different methods. One conclusion. The invisible companion pulling on that star is a black hole. They named it Omega Cat, BH2. It weighs about 4.5 times the mass of our sun. And here is the part that makes physicists sit up straight. That mass lands right in a strange and famous zone called the mass gap. It is a range between roughly 3 and 5 solar masses, where almost no black holes or neutron stars have ever been confidently detected. At least, not by gravitational wave observatories like LIGO and Virgo, which listen for the ripples in space-time produced when compact objects collide and merge. For years, some theorists have wondered whether the physics of a collapsing star simply refuses to easily produce objects in that mass range. The black hole just confirmed in Omega Centauri is sitting right in the middle of that supposedly empty zone, hiding in plain sight inside a star cluster where nobody had ever found one before. The star locked in orbit with this black hole takes roughly 94 years to complete one full trip around it. That gives the system the longest orbital period of any black hole binary anyone has ever measured. Different record, same discovery. So what does this actually prove? 3 things at once. First, that the predictions about how many black holes should be packed inside Omega Centauri were probably correct. Roughly 10,000 could really be in there. We just did not have eyes sensitive enough to spot them. Second, that the astrometry technique works inside crowded star clusters, which is exactly the kind of environment where every other method falls apart. And third, that there is now a clear path to scaling this up. The paper says it plainly. NASA's Nancy Grace Roman Space Telescope, launching in just a few weeks, will be able to scan wide, crowded fields like Omega Centauri. It will have Hubble-quality sharpness, but across a region 100 times larger, from one confirmed black hole to potentially thousands, across the densely packed central regions of the Milky Way, across other clusters, across other galaxies. A second thing worth saying out loud. There is something almost poetic about a black hole that we could not detect by listening for its roar. We found it because its companion star quietly moved a little, year after year, because of gravity nobody could see. The universe, it turns out, sometimes whispers its biggest secrets to the instruments patient enough to notice. One silent wobble in one star, captured across 20 years of patient staring, just opened the door to a population of black holes we thought might not even exist. Now let me bring you back to the room for a second before we keep going. Hey, you are still here. That means you actually care about what is happening at the edge of human knowledge. So if that is true, prove it. Smash that like button right now, harder than you have ever smashed any like button. Subscribe to this channel, ring the bell so the algorithm does not bury this in between uploads, and then drop a quick comment telling me, out of the 3 discoveries in this video, which one hit you the hardest. I read every single one, and the conversations down there have become some of my favorite parts of doing this work. Okay, onward. The second story dropped on July 27th, 2026. And it is the one that might feel the closest to home, because it is about our literal next-door neighbor in the cosmos, Andromeda, also called Messier 31, about 2.5 million light-years away, which on a universal scale is practically nothing. It is so close and so bright that on a clear, dark night with no moon and no city lights around you, you can see it with your own 2 eyes. It looks like a faint smudge of light in the constellation Andromeda, but that smudge is a spiral galaxy containing roughly 1 trillion stars. Larger than the Milky Way in many respects, and it is heading straight toward us. Our 2 galaxies are expected to merge in about 4 to 5 billion years. Because Andromeda is so similar in size and structure to our own galaxy, studying it is genuinely like looking at ourselves in a mirror held at arm's length. We can see patterns from the outside that we will never see from inside the Milky Way. A team led by Tobin Weiner at the University of Washington, working closely with Benjamin Williams and others, decided to do something nobody had ever done on this scale. They assembled the most complete star-by-star map of Andromeda ever produced by combining data from 2 enormous Hubble observing campaigns. Together, those programs are called the Panchromatic Hubble Andromeda Treasury and the Panchromatic Hubble Andromeda Southern Treasury. Across more than a decade of telescope time, with something like 600 separate Hubble pointings, they managed to measure roughly 200 million individual stars spread across about 2/3 of Andromeda's disk. 200 million stars. That is not a typo. That is 200 million points of light, each one carrying real information. Each star holds clues about when it formed, how heavy it is, how bright it burns, what its chemistry looks like. That bundle of information is essentially a fossil record. If you map enough stars in enough detail, you can read the biography of an entire galaxy. You can tell when it was young and building fast, when it had a growth spurt, when it finally started to settle down. So what does Andromeda's biography actually say? The headline finding is this. Andromeda has been losing its appetite for star formation for the last 500 million years. Honestly, it has been winding down. Right now, it is producing new stars at a rate of roughly 1/5 of our sun's mass per year. That sounds small. 500 million years ago, that rate was close to 1 full sun's mass per year, and sometimes higher. That is an 80% drop. And the trend is not slowing. Over the last 40 million years specifically, the decline has gotten even steeper than at any point in that half-billion-year slide. Andromeda is not dead. It is still making new stars, but it is doing so at a fraction of its former pace, and the curve keeps bending downward. Astronomers have a name for galaxies in this condition. They call it the green valley. It is the transitional phase between the blue spiral galaxies, full of bright young stars, and the red retired galaxies that have stopped making new ones entirely. The phrasing matters. Galaxies that enter the Green Valley do not usually camp out there. They pass through it on the way to going quiet for good. Which means Andromeda is not just resting. It is sliding toward retirement. Slowly, quietly. 500 million years is half a billion years. Why is this happening? The team's best explanation is that Andromeda has not actually run out of raw material. It still has plenty of gas that could, in principle, become new stars. The most likely story is that around 2 billion years ago, Andromeda went through a massive burst of star formation, possibly triggered by a close gravitational encounter, maybe even a partial merger with a smaller companion. That burst consumed enormous reserves of cold gas in a relatively short window of cosmic time, and the galaxy has been cooling off ever since, like a long-distance runner gasping for breath after an all-out sprint, slowly catching her wind. There is also one satellite galaxy called M32 sitting uncomfortably close to Andromeda, and astronomers are still working out whether it had a gravitational role in this whole story. That piece of the puzzle is not quite settled yet. Here is why this matters far beyond Andromeda. If our closest galactic neighbor can quietly wind down over 500 million years, the Milky Way can do the same thing. We are essentially watching a preview of what could eventually happen to our own home. The Hubble Space Telescope, when it begins operations, will be able to repeat this kind of deep survey across Andromeda in a small fraction of the time Hubble needed. That follow-up work is already being planned. Let me pause for 1 second, because I want to ask you something honest. If this video helps you understand the universe a little better than you did 5 minutes ago, do something simple for me. Share it. Send the link to a friend, post it in a group chat, drop it into a Discord server. That is the single most powerful thing that helps a channel like this keep going. Subscribe if you have not already. Bell icon, done. And if you want, leave a comment telling me what you think the next big space discovery will be. I read those, and some of you have made calls I am still thinking about months later. Now, the third story. This is the one that breaks the scale of everything else we have talked about. We are going back to the very beginning of the universe. On June 23, 2026, a team using Hubble announced the detection of ultraviolet light from a galaxy whose photons have been traveling for 12.5 billion years. To put that in perspective, the universe today is roughly 13.8 billion years old. So we are looking at light from a time when the universe was barely 10% of its current age. The galaxy existed only about 1.4 billion years after the Big Bang. The photons Hubble just captured left that galaxy when the cosmos was still, in human terms, an infant. To understand why this matters, you have to know a piece of cosmic history that almost nobody talks about outside of astronomy. After the Big Bang, the universe was a hot soup of charged particles, mostly protons and electrons, bouncing around at insane temperatures. Light could not travel anywhere because it kept slamming into those particles and scattering. Once the universe expanded enough and cooled enough, those charged particles finally combined into neutral hydrogen atoms. Suddenly, light could move freely. That moment is called recombination, and it is the source of the cosmic microwave background we still detect today. But here's the catch. Neutral hydrogen was opaque to a specific kind of light. Ultraviolet light with enough energy to ionize hydrogen could not pass through it. So the universe, even after becoming transparent to ordinary light, blocked this particular kind of radiation. Astronomers call the next billion years or so the epoch of reionization, when early stars and galaxies gradually produced enough energetic radiation to strip electrons back off, finally making the universe permanently transparent to this kind of light. That transition is one of the biggest unsolved puzzles in all of cosmology. What kind of galaxies actually drove it? How bright did they need to be? How much of their ionizing radiation actually escaped out into open space? When did the fog clear across different patches of the universe? These questions matter enormously because reionization was the last great phase transition. After it, the broad structure of the universe settled into the shape we see today. The challenge is that the galaxies responsible for that process sit so far away that they are incredibly faint. Most of the ultraviolet light they produce never makes it to us. It gets absorbed by the neutral hydrogen fog right around the galaxy. That is part of why the whole reionization process dragged on for hundreds of millions of years instead of happening overnight. So when Hubble's ultraviolet instruments picked up a clear signal from a compact, star-forming galaxy, now called LCE Z4M1, that became significant. Sitting in the famous Hubble Ultra-Deep Field around 1.4 billion years after the Big Bang, this galaxy is producing intense radiation. It is literally burning a bubble of transparency through the surrounding fog. Starlight from this galaxy is punching out into open space. In simple terms, Hubble caught a galaxy in the act of contributing directly to reionization, actively pushing the cosmic fog back. Almost everything had to line up for this detection. The galaxy's ultraviolet output had to be intense enough. The line of sight, that narrow corridor through the intergalactic medium, had to have been cleared enough by other galaxies. And Hubble's ultraviolet sensitivity, carefully preserved across nearly 4 decades, had to be sharp enough to register the signal. That combination is so rare that every confirmed detection like this is essentially a direct sample of the process that ended the cosmic dark ages. The team described it as a textbook case of the kind of object that drove Ryanization forward. And this is exactly why Hubble cannot simply be replaced by James Webb. Webb is extraordinary, the most powerful infrared space telescope ever launched. It can see redshifted light from the very earliest galaxies in stunning detail, but the specific ultraviolet photons are not part of Webb's current suite. Hubble's long-maintained ultraviolet capability, refined over 36 years of service, is, for this kind of science, genuinely irreplaceable. NASA does not treat them as the same instrument doing similar jobs. They cover different parts of the spectrum and need each other. That is what complementary means. One quick thing before we zoom out and look at the whole picture. I honestly love making videos like this. If you have made it all the way to this point, you are the exact audience I built this channel for. Go ahead and tap like one more time. It does so much more than you think. Subscribe if you are new, and then share this video with one person who would appreciate it. That is the way small channels like this keep going. From the bottom of my heart, thank you for being here. Now, let me bring all 3 stories together because the bigger picture is the one that should stay with you. Hubble launched on April 24th, 1990. It is 36 years old. Shortly after launch, scientists discovered that its primary mirror had been ground to the wrong curve. The flaw was absurdly small, about 1/50th the thickness of a human hair, but in optics, that was more than enough to blur everything. It was, in NASA's own words at the time, an embarrassment. Astronauts flew up in 1993 and fixed it during a servicing mission. That was the first of 5 separate servicing missions, each of which replaced cameras, gyroscopes, and entire instrument packages. Time after time, crews launched into orbit and brought Hubble new eyes for a telescope its critics had wanted to write off. Most space telescopes produce a few years of genuinely great results and then get superseded by something newer and more powerful. They go dark, and the archive goes quiet. Hubble has outlasted almost every expectation anyone had at launch. And it is not just surviving. It is producing science right now that nothing else on Earth or in orbit can match. That is not nostalgia, that is data. The Omega Centauri black hole required 20 years of Hubble archival data to find. The Andromeda census required more than 10 years of Hubble survey observations spread across roughly 600 separate pointings. The Ryanization galaxy detection used Hubble's specific ultraviolet sensitivity that Webb, for all its power, simply does not have. All 3 of these stories rest on the same foundation, the archive of observations that Hubble has been quietly building since the early 1990s. No new telescope starting from scratch today could recreate that history. Time itself is part of the instrument. That idea, honestly, is one of the most beautiful things about working in astronomy. The patience of the observer becomes the strength of the science. And the next chapter is almost here. NASA is preparing to launch the Nancy Grace Roman Space Telescope on August 30th, 2026. It will launch on a SpaceX Falcon Heavy rocket from Kennedy Space Center. Roman has the same size primary mirror as Hubble, 2.4 meters across, but its camera has a field of view 100 times larger. That is the leap. Hubble is like looking through a narrow picture window. Roman is like opening up an entire wall. The teams behind all 3 of these new discoveries have already said it. Roman is the instrument they have been waiting for. One confirmed black hole in Omega Centauri. Roman will go hunting for thousands across crowded fields. 2/3 of Andromeda mapped in a decade. Roman will do equivalent surveys in a small fraction of the time. One Ryanization galaxy detected against the cosmic fog. Roman will find many more, each one a window into how the universe became transparent. Hubble and Roman, working side by side, will be doing things neither could do alone. A 36-year-old observatory with an unmatched archive about to be joined by a brand new telescope, built for surveys at a scale never possible before. Together, they represent one of the most extraordinary moments in observational astronomy in decades, a bridge between the deep past and the wide present, with the same team of humans on the ground asking the same restless questions about the sky. So here is the takeaway. In 6 weeks this summer, a 36-year-old telescope produced 3 discoveries that touch on some of the deepest open questions in astronomy. Where do black holes actually come from? How do galaxies age? And what happens to them when they get old? How did the universe become transparent? And how does a machine built 36 years ago, before most of us were born, keep writing new chapters of physics in its late 30s, while a brand new telescope sits on a launch pad waiting to carry the story forward? If you stayed with me all the way to the end of this video, you now understand both the discoveries themselves and why scientists are excited. I would love for you to drop a comment below telling me which of the three hit you hardest. Subscribe if you want to stay close to the story as Roman lifts off and the next wave of results lands. And if this video changed even slightly the way you think about Hubble, about the universe, or about old machines that still do impossible things when nobody's looking, share it with someone who deserves to feel the same awe. Because that is what Hubble still gives us. Truth, after 36 years, that we did not know we were missing. And the next era of discovery is only weeks away.